Thank you so much.
Great that you, despite of all problems, you appeared online.
Mm.
Okay. Okay. Sandeep, maybe he will connect at 6:30 because his original time was 8 a.m. Boston time. It is 6:30.
Okay.
So
Okay.
then we wrote to him maybe 15 minutes before if he connects. So we have to wait.
No problem. No problem.
Thank you. Hi,
Hello, everybody.
hi. Can you hear us, Alan?
Yes, I can.
Oh, great, great, great. So I am relieved because the connection is okay.
Yeah, the connection seems good. Can
Yeah.
you
So
hear me well?
yeah. So okay. Let us begin the proceedings. I'm happy that he has joined in time because sometimes connections are not okay. So okay, I sincerely thank for Professor Guth for kindly agreeing to deliver the first Starobinsky Memorial Lecture. Professor Guth is distinguished among distinguished theoretical physicists. In fact, inflation, which he invented, led to a paradigm shift in the history of theoretical physics. Before inflation, cosmology was not considered seriously. In order to give a feeling, let me take you to my master days, 77, 78 in Moscow State University. I was in high energy physics department. Valery Rubakov was in Department of Quantum Statistics of Bogorov's department. Next to our departments, Zildovich used to teach 1 year course on structure and evolution of universe. None from our departments went to attend those lectures because at that time cosmology was not considered to be the part of physics. After inflation was invented, cosmology got integrated with high energy physics. Since then, they are going hand in hand. Not only that, today the high energy physicists actually look into cosmology for the justification of their ideas, their models. So things changed upside down. And so, who can tell you about inflation better than its inventor who is here today? So, with these words, I hand over the session to Sandeep. Sandeep, over
Okay.
to you.
Okay, well, thank you so much, Professor Sami, and warm welcome especially to our very distinguished speaker, Professor Alan Guth. Welcome, Alan. And it's really a great honor to have you here. And I also welcome all the other conference participants. And I have to make one joke, if it's a talk on the multiverse, which is I'm so glad we are all gathered in this universe here today in, if not together in space, at least in time. So, with that terrible joke, I hand it over to Alan to take us forward with his lecture, which we are all looking forward to hearing.
Sorry, I'm still setting up my computer here, but it should be ready soon. No? Okay. I'm not sure if my sharing slides is working right, but I'll get to that shortly. Let me say a few words first. It's an extreme honor for me to be speaking today at the memorial conference for Alexei Starobinsky. I've always admired Alexei tremendously. I first met Alexei way back in the summer of 1982 at a workshop in Cambridge, England called Nothing Workshop on the Growing Universe. It was organized by Stephen Hawking and Gary Gibbons. It was at that workshop that Alexei and I and several other groups were all working on the calculations of density perturbations arising from inflation. Uh, I remember having many conversations with Alexei at that time. Um, he was, I think, the only one of us who had actually finished his calculations before coming to the conference. I finished my calculations just as the conference was starting. Other people were still debating with each other during the conference. At the end, we finally all agreed on actually 4 papers that came out from that conference, all agreeing with each other. But the answer was, um, many of you probably know that Starobinsky spoke with an extreme stutter, which made him really difficult to communicate with. But it was also still apparent very early that it was well worth listening carefully to get through the study and understand what he's saying, which was always very valuable. I met Alexei again in the summer of 1989 when it was a workshop sponsored jointly by U.S. and Russian Academy of Sciences. Alexei was one of the main speakers at our meetings in Moscow. We had meetings in Moscow, D.C. And at this point, he was working mainly on implications of measurements of the cosmic magnetic background. He gave very fascinating talks about that, which I learned a great deal from. To give a little background, Alexei received his PhD in 1975, working with Yakov Zeldovich, a very prominent Russian astrophysicist and cosmologist. Alexei spent most of his career at the Landau Institute. He made, as you're probably all aware, seminal contributions to the theory of inflation. In 1979 and 1980, he published two critical papers, one of which proposed what we now call Starobinsky inflation. It was a real model of inflation, the first model of inflation that actually worked. He proposed it really for the wrong reasons. He had in mind that it would solve the initial singularity problem. He thought that the model would allow evolution going back continuously to time minus infinity. That turned out actually not true. But it was nonetheless the first successful model of inflation. And the same year, he published a second paper deriving the gravitational wave background that would result from this model of inflation, which was also a first of a kind calculation, a seminal history of inflation. Alexei won many awards. Don't want to bore you all with a long list, but include in particular the Guth Prize in Cosmology, the Dirac Medal, and also the Kavli Prize in 2014, which I enjoyed very much. We shared between Alexei, myself, and Andre Linde. We had a wonderful week in Oslo, seated by Kavli award people. In addition to his physics background, I've really only learned more recently that Alexei was very active politically in terms of resistance to the Russian political affairs. He was part of what was called the First July Club of the Russian Academy of Sciences in 2013 to resist political violence. In particular, over the years, the Russian government has more or less taken over control of the Russian Academy of Sciences. And Starobinsky's voice was one of the loudest in protest against that. And in 2022, he even had the guts, and I'm sure this required a fantastic amount of guts for someone living in Moscow. He had the guts to sign an open letter objecting to the war in Ukraine, but it was also signed by a number of other Russian scientists. It's incredibly admirable. Okay, at this point, I will switch to talking about physics. I'm not sure, as I mentioned at the beginning, if my slide show is working, but we'll see. If not, I may need to reboot. Okay, well, so alas, my things are not working. Somehow Zoom is not speaking nicely with my slideshow. So maybe there's an alternative. I can try showing my slides.
You have to find, there's a share button, Alan. It's green.
I'm well aware of that, but it's but Zoom is disappearing completely as soon as I bring up my slideshow.
I see.
But I can, I think, redo it using Acrobat, and that will hopefully work. It'll take a little bit. Audience, be patient. Speak among yourselves. Have fun.
So the Zoom icon has completely disappeared, is it, Alan?
Yeah, that's right. I'm using an unusual slides right now. Anyway, I think I'm almost ready to go now. Uh,
Ah, there we go. Something has worked.
Good. Okay, now if all is well, we can see the title slide.
Yes, we can see it.
Okay, wonderful. Okay, so what I plan to be talking about today is a subject that's near and dear to the hearts of both Alexei and me, namely inflation. And I'll talk about the basics of inflationary cosmology, and also I'll be speaking about how inflation suggests, doesn't really prove, that our universe is not the only universe, but in fact part of a much larger, possibly infinite multiverse. We'll be getting there. To begin, I want to say a few words about the standard Big Bang model, be able to contrast with inflation. The standard Big Bang model is a theory that the universe as we know it began some 13 to 14 million years ago, latest estimate being 13.80 plus or minus 0.2 billion years from the satellite collaboration. I insert these qualifying words as we know it, because we certainly don't really know that the universe began a billion years ago. There could have been a long prehistory earlier than that, but the event that we call the Big Bang certainly did happen about 13 billion years ago, and there was an event. That's pretty certain. The initial state, the state 13.8 billion years ago, was a hot, dense, uniform soup of particles that, in fact, already is assumed to have filled space uniformly, as far as we can tell, and was rapidly expanding. The matter and the entire space expanding together. This model is very successful in describing a number of things. It describes how the early universe expanded and cooled. It described how the right chemical elements formed. That is, the model starts when the universe was so hot that even the nuclei of atoms would not have been stable. So the nuclei that we see in the universe today have to form later. We believe that the latest several chemical elements were formed directly in the Big Bang itself. Heavier elements, really everything heavier than lithium, were formed much later in the history of the universe in the interior of stars. And then when stars explode, these heavier elements are spewed out into space, ready to recollect into later generations of stars. And our sun will be one of these later generations. So we are, in fact, made of stuff that was synthesized in earlier generations of stars. The classic Big Bang model also describes how the matter congealed to form stars, galaxies, and clusters of galaxies. That's still to some extent a work in progress, but a great deal is understood there. It seems to all fit together very well. I want to say some things also about what the standard Big Bang model does not describe, because that's where inflation comes in. In particular, the conventional Big Bang theory says nothing about what caused the expansion. The theory really begins its detailed description of the universe with the universe already expanding. Although it's called the Big Bang theory, it really is only the theory of the aftermath of the Big Bang. It also tells us nothing about where the matter in the universe came from. The theory assumes that really all of the matter that exists now existed from the very beginning. That is, for every particle that exists in the universe today, either that particle was there at the very beginning, or at least a precursor particle was there. from the very beginning. In other words, to summarize things, the conventional Big Bang theory really says nothing whatever about what banged, why it banged, or what happened before it banged. So those are the kinds of questions which we still don't know for sure what the answers are, but those are the kinds of questions that I will be talking about in today's discussion. So what is cosmic inflation? Cosmic inflation is a modification of the standard Big Bang theory, providing a very brief prequel to the standard Big Bang picture, to use a word that I guess was born in Hollywood. Inflation is designed to explain the bang of the Big Bang. And by that, what I mean is that it explains what propelled the Big Bang. And it turns out that inflation explains the propulsion of the Big Bang through a mechanism that I consider to be a miracle of physics, gravitational repulsion. Now, probably most of you have never heard of gravitational repulsion. Isaac Newton never heard of gravitational repulsion. In Newtonian gravity, gravity is always an attractive force. However, we now believe, in the context of general relativity, that there are circumstances under which gravity can actually act impulsively, and that is in some ways, the underlying secret behind inflationary cosmology. That is, the combination of general relativity and modern particle theories predict that at very high energies, there in fact exist many forms of matter that would create a gravitational repulsion. And inflation is essentially the assumption that the early universe contained such materials. Now, I'm calling this a miracle of physics. I'm going to be describing inflation actually as the consequence of two miracles of physics. Now, miracle is an odd word for physicists to talk about. Usually physicists never talk about miracles. But when I talk about a miracle of physics, I should define what I'm talking about. I'm talking about something that really is part of physics. A miracle of physics is an actual feature of the laws of physics as we know them. But to qualify as a miracle by my definitions, it has to meet two criteria. First of which, it should be something that was never taught to me when I was a student. And indeed, it's true, when I was a student, nobody had ever told me that gravity can sometimes act impulsively, although it had been known to me since the early days of general relativity in the early 1900s. And secondly, it should be something that's far-reaching enough in its consequences that could really change our picture of the universe. And this impulsive gravity feature of general relativity qualifies for that, at least I look at it, because it really does give us a possible explanation. It turns out an extremely plausible explanation for what drove the Big Bang, the universe that we see around us. So, to discuss this in a little bit more in detail, since the advent of general relativity, physicists have known that gravity can sometimes act impulsively. In general relativity, what creates repulsive gravity is the possibility that pressures can be negative. In general relativity, it's not just mass densities or energy densities that create gravitational fields, but in general relativity, pressures can also create gravitational fields. And pressures can actually have either sign, which is something that people are also perhaps not so terribly familiar with, but it's not really so strange either. We're used to positive pressures, the air around us, pressure, on everything. But to see a negative pressure, all we really need to do is to take, say, a piece of rubber and imagine stretching it in all directions, from all sides. The rubber will pull back, and that's a negative pressure. It's not large enough for us to see the repulsive gravity that general relativity says it must be creating, but it is a perfectly good example of the negative pressure. I'll just point out that my negative pressure line on the slide here is written in lighter gray. That's supposed to indicate that it's optional if you get confused by negative pressures. The concept seems too mind-boggling to consider at this point, you can ignore those things. The rest of the book is pretty well complete without the slightly gray sentences that are added here and there. Getting back to repulsive gravity itself, well, Einstein, in fact, used the repulsive gravity option in general relativity very early on in the form of what he called cosmological constants, which maybe they've heard of. The history is that Einstein, at this point, believed very firmly, actually, that the universe was static. He looked up in the sky, and the universe looked static. Similarly, Newton looked up in the sky, and the universe looked static. As far as I know, essentially all people who thought about cosmology from Newton through Einstein believed that the universe was static. But when Einstein put together his theory of general relativity, a new theory of gravity, and tried to apply it to the universe, he discovered that the ordinary gravity of general relativity would not allow a static universe, but rather a static universe would collapse in a very short amount of time due to the gravitational attraction of everything for everything else. But he noticed at the same time that he could add a new term to these equations, a new term to the equations that described how gravitational fields were created by matter. And this new term was consistent with all the symmetries and general properties that general relativity had. So Einstein thought it looked good. And it could create a repulsive force if it had the right sign. And he could adjust the coefficient of that term to be just right to balance the ordinary gravity of everything else to allow a static model of the universe. And this was Einstein's first model of the universe, proposed in 1917. And Einstein firmly believed this model through the late 1920s. He gave it up when he probably discovered that the universe was actually expanding, not static. In the current context, modern particle physics suggests strongly when we extrapolate our theories to super high energies that there should be many states that have negative pressures and hence create repulsive gravity, exactly like Einstein's cosmological constant did. And this is the assumption behind inflation. So, getting down to the details of inflation, inflation proposes that a patch of repulsive gravity material existed in the early universe. We still, by the way, do not really know exactly when in the history of the universe inflation happened. It was very early, but there's still a wide range of possibilities. But the most talked about range is at the energy scale of what are called grand unified theories, which is an energy scale where typical energy is 10 to the 16 GeV. And if that's the right scale, and I'll continue using numbers under that assumption, the patch would only need to have been as large as 10 to the minus 28 centimeters across. That, of course, is unbelievably small by any standards that we have today. Since the patch is going to be fantastically enlarged by inflation, the initial density or even the probability of such patches existing could have been very low. And still, if there was just one patch, it would have enlarged fantastically and taken over the universe. So that's all that seems to be needed to start inflation. A few vocabulary words here, in case some of you are not familiar with this jargon. 10 to the 16 is an abbreviation for a 1 followed by 16 zeros. The GeV, the unit of energy that I talked about just now, corresponds to almost exactly the mass energy of a single proton. And 10 to the minus 28 is a decimal point followed by 27 zeros. In any case, if we assume that such a patch exists, and that is something of an assumption, but once we assume that such a patch exists, physics that we think we understand really takes over and governs what happens from there on. The gravitational repulsion created by this material becomes the driving force behind what we now call the Big Bang. The repulsion, in fact, drives the universe, or at least this part of the universe, into a period of exponential expansion. That means that in a certain amount of time, the universe doubles in size, and Same amount of time, it doubles again. Same amount of time, it doubles yet again. And this doubling size would be estimated to be only about 10 to the minus 37 seconds, an unbelievably short length of time. The patch needs to expand by a factor of at least about 10 to the 28, which turns out takes about 100 of these doublings, in order to turn this tiny initial patch into something big enough to include the entire observed universe today. And at the end of this period of inflation, it's still very small. The region that's destined to become presently observed universe was only about the size of a marble, 70% across. Still very small compared to cosmic proportions. An important feature which allows inflation to end is that this repulsive gravity material is fundamentally unstable. It doesn't last forever. It decays in the same sense that a radioactive substance decays. That word is not mean that it rots in the biological sense, but it means it transforms into other forms of matter. And in doing so, it releases a tremendous amount of energy. And the end result is that the energy released from this repulsive gravity material forms a hot, dense, primordial soup of particles, which in fact was exactly the same starting point of the standard Big Bang model that I talked about at the beginning. So inflation, as I said at the beginning, is a prequel. Once inflation reaches this point, standard cosmology takes the root. And that has the very important feature that it means that everything that cosmologists have studying about classical cosmology is still valid in inflation. But inflation provides this prequel, which explains the initial conditions, which previously just had to be assumed out of both off, so to speak. Now, there's an important caveat here. I say that this repulsive gravity material is unstable and decays, and that does happen almost everywhere. But in fact, it is like an ordinary radioactive substance. If you have a vial of radium, it's not the case that each nucleus of radium knows it's supposed to decay after a certain length of time. That is absolutely not the case. Rather, each nucleus of radium has a certain probability of decaying at any given time, and the probability adds up to a half once you get to a half-life. But each decay is independent, and that means if you have a large number of radium atoms, some of them will decay only at a time much, much later than the half-life. And same here, some pieces of this inflating space might not decay until much, much later. That plays a role in eternal inflation, which we'll talk about later. But for now, let's focus on the simple picture, which we describe in our local universe. We believe that inflation ended at something like 10 to the minus 35 seconds or so after it started. Once this repulsive gravity material decays, the universe has been pushed into a period of extremely rapid expansion, and that continues. Inertia is a real feature of the laws of physics. But the expansion gradually slows down after this initial push due to the ordinary attractive force of gravity. An important feature, which is a bit mind-boggling, is that during this period of colossal exponential expansion, when the universe expands linearly by a factor of at least 10 to the 28, and that means that the volume, the cube of the linear size, the volume increases by at least a factor of 10 to the 84. If this region were filled with any kind of normal material, like the air in this room or anything that you're familiar with, the density of that material would have dwindled away to become totally unobservable. However, this repulsive gravity material behaves very differently, extraordinarily differently, and during this colossal expansion, the density of this repulsive gravity material is actually not lowered at all. It remains at constant value during this incredible expansion. Now that, of course, raises questions about conservation of energy. We have a fixed energy density but in the volume that's going from something that's minuscule, something that's 10 to the 84 times larger, where did the energy come from? How is it possible that energy is conserved for the energy density in this material to remain constant? Well, if you're keeping track of my counting of miracles, you may be thinking right now that this sounds like time for the next miracle. Chime in. And indeed, you're right. It's time for miracle physics number 2. You might think I'm about to tell you that energy conservation doesn't really hold, but that's not the case. As far as we know, energy conservation is exact. But the strange thing, which is probably very contrary to most people's intuition, is that energies do not always have to be positive. Energies can sometimes be negative. And in particular, rather surprisingly, the energy of the gravitational field is negative. And this is a statement that is true both in the Newtonian theory of gravity that most of you are probably familiar with, and also in general relativity. Might mention that in general relativity, it's a little harder to define what one means by total energy, including the energy of the gravitational field. So some general relativists only like to define total energy under very simplified circumstances, but others are more flexible. I go by the position that total energy is always a well-defined thing, and that if you accept that, it's always negative. There's really no doubt about how you would define it if you felt you could define it. The negative energy of gravity, then during inflation, cancel the positive energy of the increasing amount of repulsive gravity material, this exponentially expanding region, and the total energy is then constant in time and could be exactly 0. The cancellation between the negative energy of gravity and the positive energy of everything else could be exact as far as we know. That holds for the universe today as well. So even for the universe today, as well as the universe in the past, the total energy consists of a huge, shown in the black, positive contribution, all the matter and radiation and dust and stars and galaxies and everything. But there's also a huge negative contribution coming from the gravitational field that fills the universe. And we don't know exactly what the sum is, but it is consistent with being exactly 0 today, which is kind of mind-boggling to think that the whole universe might not have any net energy at all. But that does indeed appear to be the case. Okay, that finishes really the first part of my talk, where I attempted to explain what inflation is and how it works. So far, if I've gotten this across, I hopefully have persuaded you that inflation is a possible sequence of events that may have occurred in the very old universe that would be consistent with what we know about extrapolations of particle physics and general relativity being used to describe the gravitational field of the universe, space-time of the universe. What I want to do next is to talk about positive reasons for believing that it's very likely that our universe actually did this. It's not just a possible history of the universe, but in fact, very likely the actual history of the universe. So hold on to your seats, and here goes. I want to talk about 3 specific pieces of evidence for inflation. There are a few more, but they get a little technical, so we'll confine ourselves to these 3. First thing I want to talk about is the large-scale uniformity of the universe. The fact that the universe, if you look at large enough scales, looks the same essentially in all directions. The strongest evidence for this comes from the cosmic microwave background radiation, which we think of as being the leftover heat from the Big Bang. It's radiation that bathes the universe from all directions, that fills the universe. Okay? And when we measure its intensity across the sky, we find that it's uniform to the incredible accuracy of about 1 part, or at least a few parts, in 100,000. Now, this turns out to be very hard to understand in the context of conventional Big Bang cosmology without inflation. To understand why it's so hard to explain, I want to say a little bit more about the history of this radiation. It's often said that the radiation was released, back talking about that word. It's often said that the radiation was released when the universe was about 400,000 years old. In standard cosmology without inflation, I'm sorry, I'll elaborate on release first now. What we mean by released is that prior to this time, the universe was so hot that the matter in the universe was ionized. That means that the atoms are not a big dimensional atoms, but rather the electrons are ripped off, so that we have a gas of nuclei, positively charged, and electrons, negatively charged, floating through space. That's called plasma. And in this plasma phase, photons that now make up the cosmic background radiation, would constantly scatter off of these free electrons. Free electrons have a very large cross-section for scattering photons. So during the plasma phase, the photons would constantly be moving at the speed of light, but nonetheless, because they're so frequently changing directions, they would actually get nowhere. And we can think of the photons as really being frozen with the rest of the matter during the plasma phase. But at about 400,000 years after the instant creation, the universe cooled enough so that the atoms were neutralized, just neutral atoms, mainly hydrogen, some helium, traces of some other things. And these neutral atoms are highly transparent to photons. So the photons that make up the cosmic microwave background radiation today, we believe were last scattered, last interacted with matter at about 400,000 years after the Big Bang, and have just been traveling in straight lines ever since. Now, when light travels in straight lines, we're all familiar with the fact that it conveys an image. You see my face because photons bouncing off my face travel on straight lines, and this is for my webcam, and produce an image of my face, which then gets transmitted to you. So when we look at the cosmic microwave background, to a very good approximation, what we're seeing is simply a snapshot of what the universe looked like at about 400,000 years after the Big Bang. Now, in standard cosmology, we can calculate the times that all these things took. And what we find is that at about 400,000 years after the Big Bang, if the universe has started out not being completely uniform, matter and energy would have to be moved around at about 100 times the speed of light in order to smooth everything out fast enough to make the cosmic microwave background look uniform the way it does. So this is the key problem, that the early universe was uniform so early that in conventional cosmology, the only way to explain it is to assume that it started out uniform, which I should mention. You could always make that hypothesis, but if you want to explain it, then somehow you have to explain how light or energy can travel 100 times faster than light, and as far as we know, that's just impossible. This is all the story of conventional cosmology without inflation. Now, what I want to suggest is that inflation is a very simple answer to this problem. The inflationary solution comes about simply because inflation modifies the expansion history of the universe. So it inserts into the history of the universe this period of exponential expansion. And to think about what that means, I'd like to start from the present and say the universe is what's between my two hands. Now I want to follow it backwards in time. Following it backwards, it gets smaller, which the universe is expanding. But eventually we come to the ending of inflation, and going back further, the universe was expanding extraordinarily quickly, and that means going backwards and contracts incredibly quickly. And before inflation, the universe was vastly smaller than anybody would have ever considered in the context of conventional cosmology without inflation. And the idea here, to explain the uniformity, is that the uniformity can easily be established in this period just before inflation, when the entire region that's relevant was incredibly small, and there was plenty of time for it to become uniform, just in the same way that the air in this lecture hall spreads itself out evenly. Fill the lecture hall. It requires a uniform temperature. On a very small scale, these thermal equilibrium processes take over. And then what inflation does is it takes this incredibly tiny region and stretches it so that it rapidly becomes large enough to encompass everything that we see in the presently observed universe, thereby giving us what really is a very simple explanation for how the universe got to be so uniform. So that's item one, evidence for inflation. Inflation gives us a very simple explanation for the large-scale uniformity of the universe, which was otherwise not easy to explain in the context of conventional cosmology. Next problem that I want to talk about is what is referred to as the flatness problem. It's the problem of why was the early universe so flat? Flat here does not mean two-dimensional, as it might sound. Flat refers to the geometry being Euclidean as opposed to curved space. If we assume that the universe is homogeneous, which means it's the same in all places, and if we also assume that it's isotropic, meaning it's the same in all directions, and both of these assumptions are standard parts of cosmology long before inflation, in terms of the properties of the real universe scales. If we make those assumptions, then general relativity tells us that there are only three possible geometries, and they're most easily described in terms of two-dimensional analogs, two-dimensional surfaces, where a closed geometry is analogous to the surface of a sphere. An open geometry is analogous to a saddle-shaped thing, shown on the slide here, and a flat geometry is exactly the flat geometry of Euclidean geometry, the geometry that we learned about in high school. Now, the reason we all learned about Euclidean geometry in high school is that the universe certainly is at least incredibly close to being Euclidean. But we still don't know whether or not there is some curvature, either possibly closed or possibly open on much larger scales that it's hard to observe. And this flatness problem is a problem associated with the degree of flatness of the universe at the very early stage. I don't want to get clear why that's a problem. In the context of general relativity, the flatness of the universe ends up being related to its mass density. Cosmologists define a quantity called omega, capital Greek letter omega, which is just defined to be the actual mass density of the universe on average, divided by what's called the critical mass density. The critical mass density depends on the expansion rate. It's not a universal constant, but for a given expansion rate, there's a particular mass density which puts the universe just on the border of being open or closed. That is, causes the universe to be flat. That's border in that case. And that's called the critical mass density. So omega measures how close the universe is to flat. If omega is 1, it means the universe is exactly flat. If omega is bigger than 1, it means the universe is closed. If the universe is less than 1, it means the universe is open. Now, the strange thing about the behavior of omega is that it changes as the universe evolves. And furthermore, the way in which it changes is rather odd. It turns out that omega equals 1 is what is technically called an unstable equilibrium point. And does sound like perhaps highfalutin words, but what it means is just that it's like a pencil bouncing on its tip. If a pencil is balanced perfectly on its tip, and we use classical physics, quantum physics actually messes this up. If we imagine classical physics governing this pencil, if it's exactly straight up, it won't know which way to fall, and it will remain exactly straight up forever. But if it gets just the slightest nudge in either direction, it will rapidly fall over in whatever direction you see the nudge. It turns out that omega equals 1 in the early universe behaves the same way. That is, if omega in the early universe was just slightly below 1, it would rapidly fall to 0, and no galaxies would form, and of course there would not be time. The universe would just thin out too quickly. If omega in the early universe were just slightly greater than 1, then it rapidly rises, in fact rises all the way to infinity. Omega equals infinity corresponds to a closed universe that has reached its maximum size. The closed universe reaches its maximum size and then turns around and collapses. And again, this would happen too quickly for any galaxies or life to form. And I might just add here, if it's not clear, if omega is exactly equal to 1, it will stay exactly equal to 1 forever, just like the pencil, straight up. To be a bit more quantitative, if all we knew was that today the universe was within a factor of 10 in this critical density, and this is sort of relevant because this problem was talked about eventually about 1980, but that was about what was known about the current mass density of the universe. But even if that's all we knew, if we extrapolate back to 1 second, because of this instability, at 1 second, omega had to be extraordinarily close to 1, and we can calculate how close that means. And the answer is it has to be equal to 1 to the extraordinary accuracy of 15 decimal places. Now, that would be fine if there was a way to explain why omega started out so incredibly close to 1. But in conventional cosmology, there's no way to explain it. Conventional cosmology just puts the initial value of omega as an initial condition to be specified arbitrarily. The model does not contain anything, any way, method of specifying the initial conditions. So in conventional cosmology, this extraordinarily fine-tuned value of omega had to simply be assumed out of whole cloth, because that's what needed if the universe is going to end up looking anything like it looks like today. Inflation solves that problem, meaning it gives us an explanation of why omega started out so extraordinarily close to 1. And the explanation, again, hinges on this peculiar behavior of repulsive gravity. The behavior of omega that I described before is the behavior of omega in the presence of attractive gravity, which describes all of the history of the universe, actually up to recently, we'll talk about later, but describes most of the history of the universe and certainly all the history of the universe shortly after inflation, and all the history of the universe known around 1980. But the repulsive gravity implied by inflation turns out behaves exactly in the opposite way. During inflation, instead of being driven away from 1, omega is driven towards 1. In fact, it's driven towards 1 incredibly rapidly. So if one has inflation, it means that before inflation, omega did not have to be extraordinarily close to 1 or close to 1 at all. Could have been 2 or 10 or even 100. The larger it starts out, or the smaller it starts out, the further from 1 it starts out, the more inflation you need to drive it to 1 successfully. But that's easy to get in the models. So inflation is capable of solving the riddle of why omega in the early universe chose this value so extraordinarily close to the number 1. Now, this also leads to a prediction. Since the mechanism by which inflation explains this flatness problem, the mechanism by which explains why omega is very near 1, almost always overshoots, the most inflation means just the right time, it predicts that even today the universe should have a critical density. That is, today the universe should still have 1. Historically, this was initially a problem for inflation until about 1998, or maybe I shouldn't say until exactly 1998. Observation was pointing towards a value of omega of 0.2 and 0.3. Turns out it's hard to measure, so it's always a bit controversial. So omega equals 1 was not considered, ruled out by everybody in 1998, but the astronomical community as a whole is certainly converging on values like 0.2 and 0.3. So this was uncomfortable for the theory of inflation. And I can add on a personal note that this also made it very uncomfortable for me to have dinner with astronomers during the 1990s. Astronomers would typically look at me and sneer a little bit and say that they do regard inflation as being a very beautiful theory, but it doesn't seem to be what the universe is doing. Thus, inflation predicts a negative 1. They assured me there was mounting and mounting evidence that the real universe did not have negative 1. However, inflation has the last laugh. Starting in 1998, everything changed, and I'll explain in a minute the reason for that change. And now, observationally, omega is known to be incredibly close to 1, just like inflation predicts. The best number to date comes from this Planck satellite collaboration from 2015 data, which is the final data set. And they find that omega is, they can't show it's exactly 1, but they show it's 0.9993 plus or minus 0.0037 to 95% confidence. So they believe there's a 95% chance that it lies in that range and 25% chance that it might be outside that range. So this confirms that omega equals 1 to an accuracy of better than 0.5%. So now, observationally, we do find omega sure looks like it's 1. The important change, which we need to make sense out of all this, is that in 1998, it was discovered by 2 important groups of astronomers independently that the universe is not currently slowing down under the influence of gravity, but apparently for about the last 5 billion years, the universe has actually been accelerating in its expansion. This is a phenomenon very much like inflation. In fact, we explain it in the same language as inflation. Explain it in terms of repulsive gravity coming out of general relativity. At least that's the most widely accepted explanation. And the repulsive gravity material, we're still not quite sure how to identify it. The name dark energy has been made up to describe the repulsive gravity material that appears to be filling our universe, whatever it is, we call it dark energy. And we can calculate how much of it is because we know how much it's accelerating the universe. And when we add that in, that's what gives us this current number for omega being incredibly close, up to 1, as inflation predicts. So big success for inflation. All right, so that's my second piece of evidence for inflation. Large-scale uniformity, the flatness problem. Moving on, the next and last success of inflation that I want to talk about is the small-scale non-uniformity of the universe. I mentioned earlier that this cosmic microwave background radiation, which we measure coming from the sky, has an intensity that's almost uniform in all directions, uniform to about a few parts in 1,000. But at the level of a few parts in 100,000, there actually are visible non-uniformities. Visible now, these are incredibly precise instruments, quite visible. So these ripples are now very carefully measured by physicists, astrophysicists, and we know about their properties, but there's the question of where did they come from? They are, by the way, essential to our picture of the universe, not just oddities that were discovered by very sensitive instruments. They're essential because they are needed for our understanding of how galaxies form. Galaxies form, as we understand it, by gravitational instability starting from these ripples. That is, in regions of the ripples with a slightly higher than average density of matter, that creates a slightly stronger local gravitational field which pulls in more matter, creating a still stronger gravitational field, pulling in more matter, and that cascades and ultimately leads to the formation of galaxies and stars and all of the structure of the universe. So these non-uniformities are very essential to our understanding. But in conventional cosmology, before inflation, nobody had the foggiest idea of where these ripples might come from. Basically, nobody had the foggiest idea where the uniformity came from, so naturally, there's no discussing deviations from it. But it turns out that inflation has a spectacular answer to this question. Spectacular in the sense that it does work very well, as I'll show you in a minute, but also spectacular in the sense that it evokes rather mind-boggling concepts of modern physics. Inflation attributes these ripples to quantum behavior, to what are called quantum fluctuations. The key feature here of quantum theory is that, unlike classical theory, quantum theory is not entirely predictive, but rather only allows the prediction of probabilities. So for almost any result that one can make a classical prediction for, quantum mechanics tells us that that classical prediction might be what will happen on average, but very precise experiments, sometimes you get it higher, sometimes lower, and there'll be a well-defined distribution of probabilities that quantum mechanics allows us to predict. So the early work on inflation was in fact done purely classically, and there was a period of several years where those of us working on inflation were very worried that inflation would just smooth the universe out completely, the way that Alexei explained. But then it was realized in several different quarters that quantum physics could come to our rescue. If the classical picture is predicting a perfectly uniform probability distribution across, if the classical picture is predicting a perfectly uniform density across space, the quantum picture will predict that in some regions the actual density will be a little bit above this classically predicted average, and in other regions the density will be a little bit below this classically predicted average, and that will give us precisely this system of faint ripples on this almost uniform background. And we can actually do calculations. The calculations depend somewhat on the details of inflation, which are not firmly pinned down. Inflation is really based on extrapolation of physics to much higher energies, so we don't know details. We don't know features that are common to many different extrapolations. And in this case, what those extrapolations tell us is that the overall intensity of these fluctuations is something that depends on the details. We can't, at this stage, make a prediction for. If we know all the physics, inflation would allow a prediction, but we don't know enough about the underlying particle physics to make a prediction for the intensity. So we just take that as what we measure in the cosmic microwave background. But then inflation, or at least a large class of very plausible models of inflation, make the same prediction for what's called the spectrum of the fluctuations. And by spectrum, what I mean is pretty much the same thing as what one means when one talks about the spectrum of sound waves. What I mean is how the intensity of these ripples varies with the wavelength. And in this case, the wavelength is measured at an angle in the sky. So it's out of the sky, so it's an angular wavelength. But it's nonetheless a wavelength that we can measure. We talk about the intensity of ripples for different values of this wavelength. So first, a picture of what the ripples look like. This is a false color image. And that means that if you saw the real picture, the variations across would only be a few parts in 100,000. Your eyes will tell you it just looks completely bland and uniform. But what's done here is to amplify those small deviations in intensity and temperature to reflect them in different colors. It allows you to see this very complex pattern that has been measured. This is the pattern that satellite. This oval is a map of the entire sky, projection that's similar to what's sometimes used for maps of the surface of the Earth. This is the spectrum that I was talking about. So let me amplify what's being plotted here. On the vertical axis is the temperature fluctuations. These are like squared fluctuations measured at microkelvin squared. And on the horizontal axis is the angular scale I talked about, the angular wavelength, going from long wavelength on the left to very short wavelength on the right. For those of you who know about spherical harmonics and multipoles, this is actually measured in terms of multiple moments, L, which is shown in the top, but it really is equivalent to this angular wavelength scale, which is important to understand. The dots here are the actual measurements coming from the Planck satellite. And the blue line that seems to go through the dots magnificently is a line based on predictions of a simple inflationary model. The model has 6 free numbers that are adjusted to optimize this fed. But 6 numbers is not enough to explain a curve as complicated as this. So it's certainly regarded as a magnificent success of inflationary cosmology. And I might mention there are 6 numbers, at least 4 of them are numbers that we have good predictions for from other places, and everything is perfectly consistent. Only 2 of them that fit to the data. One of those is what I want to mention. The amplitude, the overall height, is just fit to the data. There's no inflationary prediction at this stage in the overall height of this curve. But spectacular success. Okay, now I want to move to the final phase of my talk. I want to talk about how inflation suggests the existence of a multiverse. There are a few points here. First important point is that almost all detailed models of inflation lead to what is called eternal inflation, which in turn leads to multiverse. And this is fairly simple to understand in terms of this idea of the repulsive gravity state decaying like a radioactive substance, which I simplifying the picture a little bit, inflation is driven by this repulsive gravity material, which is only metastable, it's not completely stable. So you can imagine waiting for a half-life of the decay of this material. It does decay with a half-life, much like radioactive materials. And if you do, by definition, half of the region you were looking at will decay, half will not decay, on average at least. But the key thing that makes this very, very different from the decay while radium is that while the decay is happening, the exponential expansion is also happening. And in fact, the exponential expansion is much, much faster than the exponential decay. So if you wait for one half-life of the decay, that turns out to be many, many doubling times of the expansion. And at the end, even though half of the region that you initially started looking at would still be inflating, its volume would actually be vastly larger than the inflating volume at the beginning because of the exponential expansion. And if we continue this into the future, as far as we can tell, it goes on forever. Forever is, of course, a strong thing for any theoretical physicist to predict, so we don't really know about forever. But we can say we don't know what's going to ever stop this. It may go on forever. And places where these decays happen, which can happen sporadically, randomly, in different places in space and time, the places where these decays happen, each one will form a universe, much like our universe. And we refer to these as pocket universes. But the phrase pocket universe is just intended to convey the idea that this is not the entire universe, but construction, multiverse, of a large number, perhaps an infinite number of pocket universes. We would be living in one of these possibly infinite universes. Now, this turns out to actually be relevant to some problems in physics. It could be just science fiction, and some people think that's something like always do think it's just science fiction. But many of us think that it is a plausible physical scenario, and also one that is relevant to important physics problems. And the most salient of those is what is called the cosmological constant problem. I mentioned earlier that in 1998, 2 groups of astronomers discovered that the universe today is accelerating. According to general relativity, that requires the universe to be filled is a repulsive gravity material, which we can also identify as negative pressure material. And whatever it is, it's called dark energy. And the simplest explanation is that this dark energy is just vacuum energy, the energy density of empty space. I should mention here that the physicist vacuum is far from empty. The physicist vacuum is actually a very complicated system where quantum fields are undergoing fluctuations. For example, the electromagnetic field in the vacuum is constantly undergoing fluctuations, really driven by the uncertainty principle of quantum mechanics. In addition, in the vacuum, we believe electron-positron pairs are constantly materializing and disappearing. We also believe that in the vacuum, there's at least one field, Higgs field, of the standard model of particle physics, where this Higgs field has a non-zero value without space, which is really an essential part of understanding this standard model of particle physics, how it works. So it's not particularly surprising to theoretical physicists that the vacuum might have non-zero density of energy, but the actual value it has really makes no sense to us. We don't know how to calculate what the vacuum energy should be, but we think we know how to estimate it crudely. And when we do that, what we find is that our estimates are vastly larger than the observed value. In fact, larger by highly embarrassing 120 orders of magnitude, making this presumably the most spectacular failure of theoretical predictions or theoretical physics. So why is the observed value of the cosmological constant so incredibly small? And when I interchange these words, cosmological constant and vacuum energy density, explain that yet, but physicists do regard those words as synonymous. It turns out that the cosmological constant term that Einstein added to equations has exactly the same form as what you would add as the vacuum at a non-zero density. That is how we now interpret Einstein's cosmological term. So it turns out that the multiverse does offer a possible, although I should honestly admit, very controversial explanation of why the energy density of our vacuum is 120 orders of magnitude or so smaller than the expected value. The expected value is often referred to as the Planck scale. The way inflation explains this is that if inflation can be combined with a theory where there are many different types of vacuum, and in fact, string theory, which we regard as almost certainly our best attempt at a quantum theory of gravity, string theory predicts that there should be a huge collection of possible vacuum-like states, 10 to the 500 or possibly vastly more. And each of them would have their own vacuum energy density. They'd all be slightly different in their internal structure, giving rise to different vacuum energy densities. And that means if there were so many, some of them would have incredibly small vacuum energy densities, like the one that we are living in. But then there's still the question of why, if only a tiny fraction of these vacua have such a small vacuum energy, why should we expect to find ourselves in such a rare example of the vacuum? But there is an answer to that. The answer is that this does have important implications for the formation of life. This cosmological constant or vacuum energy is directly related to the acceleration of the universe, which is how we discovered in the first place. And if the vacuum energy were very large and positive, it would cause the universe to fly apart in a tiny fraction of a second, far faster than would allow the possibility of galaxies to ever form. And similarly, if this vacuum energy were large but negative, which is also a possibility as far as we know, that would lead to a universe that would implode in a tiny fraction of a second, far faster than light ever formed. So it becomes very plausible that life can only form in those rarer pocket universes where the vacuum energy is incredibly small, like ours. And if that's the case, then it would mean that even though in most of the multiverse, the cosmological constant would be vastly larger than what we observe, it would still turn out that all living beings in this multiverse would in fact measure a very small value of the cosmological constant. And that seems to be enough to explain what current observations. So that's the argument. The multiverse can help explain why the observed cosmological constant is so small. Let me quickly summarize, and then there's one fast point I want to make. To summarize what I said about inflation, by and large, the inflationary paradigm is in great shape. It explains the large-scale uniformity of the universe. It predicts the mass density of the universe to better than 1% accuracy. And it also explains and gives a very accurate picture of the patterns that we see in the ripples of the cosmic microwave background radiation, explaining this phenomenon in terms of quantum physics, which is, I find, rather mind-boggling. I also talked about tendency toward the multiverse. I didn't count them as I said them, but there are really three where I refer to here as strong winds blowing in the favor of the multiverse. First comes from theoretical cosmology, the fact that almost all the inflationary models are eternal into the future, meaning once inflation starts, it never stops. It goes on forever, producing more and more pocket universes. There's also the important fact from observational cosmology that we now know that the universe appears to have a non-zero cosmological constant or vacuum energy density, but it's incredibly much smaller than particle theorists would have expected. Why? And finally, we have an important development from string theory, that string theory predicts a huge number of different vacuum-like states, which sets up the perfect situation to apply these anthropic selection arguments that life only forms when constant vacuum energy density is incredibly small. I want to close with just a sort of a sociological discussion here, which will be brief, but I want to discuss the question of how seriously do physicists actually take this multiverse idea. Bottom line is, it depends who you ask. And in fact, several years ago, there was a conference about the multiverse where journalists went around asking people how much they would bet on the multiverse. And I'll quote a few of the answers that they obtained. Martin Rees, who may not be well known to many of you, but he's incredibly important theoretical astrophysicist. He's been knighted in England. He's the Astronomer Royal of Great Britain. He's a former president of the Royal Society, former master of Trinity College at Cambridge University, the winner of the Gruber Prize, the Popper Prize, the Templeton Prize, the Newton Prize. He's won more or less everything except the Nobel Prize. And he's a fan of the multiverse. He's written about the multiverse. And he said that he's sufficiently confident about the multiverse to bet his dog's life on it. Now, I have to admit, I never met Martin Rees's dog, but I assume it's probably a very cute dog. This is a very serious bet on Martin Rees's part. The next person I want to talk about is Andre Lindgren, the other pioneer of inflationary cosmology. Andre is at Stanford University and certainly played a major role with the early development of inflationary cosmology. He also has won many prizes, including the Dirac Prize, the Guth Prize, both of which were also won by Starobinsky, by the way, the 2012 Fundamental Physics Prize, and as I think I already mentioned, the 2014 Kavli Prize, which was awarded to Alexei. Me. Andre is a huge enthusiast for the multiverse. So he, perhaps not surprisingly to those of us who know him, said that he's so confident that he would bet his own life on the existence of the multiverse. Certainly huge stakes. Finally, I want to mention Stephen Weinberg, who was actually not at the conference, but commented about it later in an article he wrote. Stephen Weinberg is someone who I always regarded as the voice of reason in theoretical physics. And he's also worked on the multiverse. In fact, he was the one who did the primary calculations of how small vacuum energy would have to be for galaxies to form. He also has many, many prizes, including the Nobel Prize and the other prizes listed here. And he said that he has just enough confidence in the multiverse to bet. I think of something very clever here. Steve is very clever. He said he has just enough confidence to bet the lives of both Andre Linde and Martin Rees's dog. So I'll stop there. Thank you.
Thank you very much, Alan, for a really great and very comprehensive review of inflationary cosmology and also leading up to the more recent developments in the multiverse. And thank you also for talking about string theory as a string theorist and for what that is also telling us. And I think it's very exciting as our ideas, as you said, from observation and quantum gravity and so on, all seem to be converging towards substantiating your beautiful idea of inflation. So I think I am actually going to hand over to Professor Sami because unfortunately I'm not there in person at the conference. So Professor Sami, please.
Okay. Well, so let us have questions, and you have great possibility to ask him. He's the inventor of inflation. Hardly you meet such a person, right? So, okay.
Sir, what is the initial condition to inflation start?
Okay, question in case not everybody here is what initial conditions are required for inflation to start? That remains a controversial subject and certainly a very difficult question to try to address since we don't actually have any theory of the actual origin of the universe. I should have perhaps emphasized that inflation is not a theory of the origin of the universe, but only a theory of the very early evolution of the universe. Crudely speaking, what one needs is a region of space where the energy density is high enough, preferably at this grain unified theory scale, but there are versions of inflation that happen at much lower scales as well. And the region has to be approximately the size of the Hubble horizon, that is, whatever the expansion rate is, the inverse of that expansion rate each time, speed of light, Hubble length. The region has to be of that size or perhaps a little bit larger. And certainly people are studying this. It depends on details of what you've seen about the initial non-quantities. That becomes a hard problem. My own take is that I consider it very likely that inflation is eternal, as I just described. And if inflation is eternal, it means it only has to have started once in all of eternity. And the probability of that, it seems to me, is one, no matter how small the probability of any individual event is. I sometimes point out the analogy with the origin of life. Nobody thinks it's probable that it goes together, nitrogen, carbon, best even shakes it up. Nobody thinks it's very probable that it gets anyone that materials at all, DNA. But think that over the Earth, it's reasonable to assume that it happened. Similarly, I think over all of eternity, it's reasonable to assume that inflation would start. And the key feature of inflation, that to me makes it seem very plausible, is that once it starts, it seems to obviously take over whatever else you might assume becomes just irrelevant to exponential expansion at a very rapid rate. Inflation.
Thank you, Professor Guth, for this wonderful talk. My question is that we already know that as we invented that at the very early time of the universe, we need an inflation and accelerated period of expansion. But we also know now that there is also another accelerated period of expansion at the very late time of the universe. What your thought about whether these two accelerating universe can in any way be related, or like, do you have any thought about that?
Okay, very interesting question. Is there a relationship between inflation in the early universe and the current acceleration of the universe? Certainly, the bottom line answer is we don't know, but still I'll speculate. Certainly, in some sense, the underlying mechanism is almost certainly the same. Material with a negative pressure that creates repulsive gravity that causes the universe to accelerate. In the context of general relativity, which seems to be the right theory of gravity, that's really what happened. So they have that much in common. Now, in more detail, I didn't get into in today's talk because I wanted to keep it accessible, but the inflation is usually assumed to be driven by what's called the scalar field. And there is the question of, could it be that the same scalar field that was responsible for inflation in the early universe is doing it again now? And there is a possibility of that, certainly. There was, in fact, a paper by Jim Peebles and Alexei that proposed a detailed model of exactly that. That certainly seems to be a possible model of the universe. But I would also say that given string theory and ideas about supersymmetry in particle theory, there doesn't seem to be any shortage of scalar fields. So I would say that assuming that the full laws of physics became a very large number of scalar fields, which looks very plausible, very likely the scalar field responsible for inflation is not the same scalar field that's driving the acceleration of the universe today.
I'm not hearing any more questions, Professor Sami.
Yeah, so I have a query. Okay. I have really a confusion regarding the initial conditions. So Willinkin, Longback, and now the Steinhardt repeatedly pointed out that the probability measure of generic initial conditions that would lead to inflation is very small. So what do you think about it? According to them, it is not easy to get to inflation because the probability measure of the initial condition they call generic is very small. What do you think about that?
Okay, well, as I said, it's a controversial subject. By and large, whenever groups who are interested in inflation do experiments with random initial conditions to see how often inflation starts, they typically find that inflation is very likely to start. While groups who are trying to advocate their own theories, like Steinhardt and cyclic and erotic model, try to simulate it, they find low probabilities. And an important feature is we don't really know what probability distributions, densities, and density perturbations to start with. So I think you really can get into at this stage. I think ultimately we may have some real theory of a quantum origin of the universe that will answer this question. But as I said before, I don't think there's really any reason to worry about how small the probability of inflation starting is from random initial conditions. It only has to start once in all of eternity. And the key feature that still makes it incredibly robust is that once inflation starts, it really does just take over the universe in a way that seems like there's no way to stop it. So if it happened once in all of eternity, I think we would still expect, even if it was only once, I think we would still expect that the universe we would find ourselves living in would be a universe that was the aftermath of inflation.
Okay, if there is no other question, So let us thank Alan for a memorable talk and very inspiring talk that we have had from him. I'm also thankful to Sandeep for chairing this session.
Thank you so much. Thank you, Alan, for a wonderful talk, and thank you, Professor Sam.
Thank you, Alan. Thanks a lot.